How do you do, ladies and gentlemen, and teachers and boys and girls? I'm Julius Sumner Miller, and physics is my business. And my special business today is entitled Electrostatic Phenomena, Foundations of Electricity. The experiments I will do are absolutely trivial in their nature, but absolutely profound in their meaning. Consider the following. In the 5th century BC, a Greek by the name of Thales made an utterance of this sort. If amber is rubbed, it acquires the property of attracting unto itself light bits of straw and dust. And would you believe it, this was the beginning of all that we have in electricity and magnetism. As an illustration of it, here I have a hard rubber rod. I am handling it so that it is, as we say, electrostatically neutral. No excess charge of any sort. Identical numbers of positive and negative electricity. I approach it to some cork dust. I approach it, and we see nothing happen. Nothing. Nothing. Now that nothing is a very significant thing. Indeed, when experiments reveal nothing happening, they are often regarded as failures. But I must remind you, a classic in our history, when at the turn of this century, Michelson and Morley did a famous experiment on the so-called ether drift. The results they got were nil, and they thought the experiment failed. But the genius Einstein took a hold of that so-called failure, and out of that was born relativity. So let's go back. The rod is electrostatically neutral. There is no interaction between the rod and the cork dust. Now I am going to do something. Trivial, really. Piece of fur. The rod has acquired astonishing electrostatic properties. Watch it now. Watch it. I approach it to the cork dust. Ho, 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 ho! Cork dust is gathered. And if we can look closely, very closely, we see an astonishing thing. Let me point out on the blackboard, on my writing board, what we really have seen. There is the rod. There is some cork dust. The rod did nothing to the cork dust in the beginning. Then I charged the rod. By the mechanical action, I separated charges. So the rod has, by definition on it, a negative charge. And you notice I'm making many negative charges on the sharp point. Very significant. Charge density is greatest at sharp points, and we shall later learn that's why Benjamin Franklin suggested pointed rods for lightning arrestors. Now what happened? Some of the cork dust got pulled up by actions I will not trouble you with here. So here's the cork dust on the rod. Then after a moment, what did we see? We saw the cork dust jump away. Jump away. That's the significant thing in two parts. One, it was first attracted to the rod. Two, after a moment, it jumped away. I'll not annoy you with any discourse on the physics. This you can explore in the classroom. Consider now a comb, electrostatically neutral. Let me bring it near some paper, little bits of paper, some confetti. And we see nothing happens, nothing. Now, let me rub that comb through my hair. Mad physicist's hair. Watch it now, watch it. Oh, notice, I must either be lifeless or of low voltage. Let me try this on here. Oh, why didn't this work? I think I know why it worked. Why it didn't work. My hair is a little damp, and water vapor is a very, very bad insulator. It's a good conductor. So, watch it now. Ha-ha, there we are, there we are, there we are. Some of the paper. A wonderful experiment which you can explore in the classroom. Now, we define the charge on the rubber rod rubbed with fur as negative. Similarly, if we rubbed a glass rod with silk, we would define the charge on the rod as positive. This is a point of departure. Now I have an instrument called an electroscope. Let me draw it for you. a metal rod, a metal knob, a metal knob, a metal rod, and a sliver of light gold foil right there. Now, I am going to make this system electrostatically neutral. Notice I'm having a little trouble. The charges are so abundant here. The gold sliver lies close against the metal rod. Now I am going to rub the rubber rod on the cat's fur and approach. Watch. What? Ho ho, ho ho. I'm going to turn this. I think this will show better here. There it is. There it is. There it is. And the nearer I get, the greater the electrostatic forces. Now, I'm going to deposit some of this negative charge on that electroscope knob, and the electroscope is permanently charged. Except that, if you will give me your undivided attention, except that the charge will diminish as time goes because of radiation that produces ionization in this room. The charge will, as is sometimes said, leak off. Now that electroscope is charged negatively by conduction. Conduction. Negatively by conduction. Question, what can I do with it? I can determine the nature of an unknown charge. I don't know what the charge is on this comb, but watch what the electroscope does. Watch it. The leaf diverges further, and by a little analysis, I could decide what the charge on the comb is. Now, I have charged, oh, notice, this is amazing. I am excessively charged myself, which means that I am now high voltage. Oh, that's a good one, isn't it? High voltage. I have discharged the electroscope again. Remember, when I made contact, I said that the electroscope was charged by conduction. Now I'm going to charge it another way. Watch. Watch. Rubber rod, negative. I'm going to bring the rod near the knob. The leaf diverges. The leaf diverges. I'm not making any connection. Now I am going to ground the electroscope. The leaf collapsed. Pretty nearly. Now I'm going to take my hand away. Now I'm going to take the rod away. And you see that the electroscope is substantially charged, and the charging this time is by induction. And I'm going to tell you, for your own edification, that when I charged the electroscope by conduction with a negative rod, it had a negative charge on it. When I charged the electroscope by induction, it had an opposite charge. That is, it's now charged positively. I'm going to prove that. Watch. Proof. Watch it. Notice the leaf collapses. That proves to me that the charge there is positive. Now, another very dramatic thing. Here I have two little wads of paper. Can they be seen? Maybe seen better over here. Maybe seen better. Where are they? Yes, two little wads of paper. They are electrostatically neutral because I have touched them and grounded them. Now I'm going to approach them with a charged rod. Watch what happens. Watch what happens. I'm going to approach them with a charged rod. They will make connection with the charged rod because of induction. They will instantly acquire a charge like that on the rod. And watch their wonderful behavior. Watch it now. Watch. Watch it. There we are. They made instantaneous connection, and now they are rushing away with all fright from their kin, since like charges repel. Look at that. Isn't that fantastic? All right. Now, I have shown you how to charge an electroscope by conduction, how to charge an electroscope by induction, and the wonderful behavior of charges plus and minus, or positive and negative. Question. In a lightning storm, charge arises in great abundance on clouds and on the earth. A good protection against electric fields, which arise from great charge density, is the following. You remember, when I have this electroscope, or one such, here is another one, with a leaf on it. If you get closely, you'll see there's a gold leaf. There it is, there it is. There it is. There it is. There it is, right? Now, that electroscope suffers the influence of this electric field produced by this charged rod. How can I protect it from these stray fields? Answer. Here is a wire cage just made of window screening. I have put an electroscope in here, and it matters not how intense the electric fields outside, the region inside would be field-free. And hence, where would be the safest place in a lightning storm? In a steel railroad car or some such. Something for you to think about. Now, another dramatic experiment to show you the enormous forces that arise when bodies are charged. Here I have a slab of wood. It could be as big as a 2x4 or a 6x8 or a 12x20 and 100 feet long. I have set it nicely in balance on a watch glass. Piece of dry wood, so that it's free to move in a horizontal plane. Now, what would I do? I am going to charge the end of this stick in such a manner. Somebody says he looks like a mad physicist. Yeah, sure. I am doing some work and thus separating electric charges so that the wood now has on its surface one kind of charge and the fur the opposite kind. Now I'm balancing it again, and I'm hoping, of course, that the wood is a poor conductor. Otherwise, I would have grounded it by handling it. Now I'm going to charge the metal, the rubber rod, and watch. Watch. Watch closely. Oh, somebody says it ain't turning, which I had expected it to do. Why? The experiment failed. No, you know I'd blow my stack with that refrain. It did not fail. Apparently friction is too great here, and the electric force is too small. But I urge you to try it. It is very dramatic. A 2x4 can be moved by the strength of the electric field produced by a charged rubber rod. So, coming back to our beginning, all I have done is rub some stuff with some stuff, and thus giving rise to a separation of charges, and thus the foundations of all electrical phenomena, which makes everything we have today possible. Merely these charges arising from the confluence of different materials. And so I thank you for your attention, and I shall return another day.